You've already been introduced to intramolecular aldol reactions in your puzzle last week, and you've had 50 minutes kind of thinking through what are the possibilities. But I wanted to at least kind of work through an example with you and highlight the thought process. So as you know, if a compound has two carbonyls in it, then one of them potentially could form an enolate, and that enolate is a nucleophile and could react with the other one. So again, if we have sodium hydroxide in solution with it, then a certain percentage of the acidic hydrogens will be deprotonated at any given time. So let's look at our compound here. It's actually symmetrical, ethyl group on this end, ethyl on that end. We have two different kinds of alpha hydrogens, the ones that are on the ethyl group and the ones that are in the middle of the chain. And so these two are identical. All these four hydrogens are identical alpha hydrogens, and then these four out here are identical alpha hydrogens. So let's pull off one of these alpha hydrogens and make an enolate on one end and kind of think through what happens as it reacts. So we have our carbonyl at this end, and we'll make the enolate at the other end here. So first thing that we want to do, if we are going to make a product, especially one that's forming a ring, is to number our carbons. So this enolate right here then potentially could react with this carbonyl and form a ring. How many members would be in the ring? 1, 2, 3, 4, 5-membered ring. And this is what you need to keep in mind, and this is what I told you on the puzzle last week, that if it can form a 5 or 6-membered ring, it will. If it would form a 4 or 3-membered ring or 7 or 8-membered ring, it wouldn't. And this is a rate thing. So let's go ahead and number here. 1, 2, 3, 4, 5, 6, 7, 8. And so if we're going to form the product from that, then we will form, as we already said, 1, 2, 3, 4, 5-membered ring. So if I'm drawing the product, first thing I'm going to do is draw a 5-membered ring. And then I'm going to number that ring by the carbons that are in it, 2, 3, 4, 5, 6, right? So 2, 3, 4, 5, 6, and then let's see what else is on there, where the carbonyl is, where whatever. Okay, so 2 is bonding to 6. What kind of bond is between 2 and 6 in the final product? Remember, the enolate is bonding to the carbonyl. We're losing molecule of water. This is becoming a double bond. And so between 2 and 6, this is the new double bond that is forming. On carbon 2, we also have carbon 1 hanging off, methyl group. On carbon 3, it's not reacting at all. We have a carbonyl. And then we have carbons 4, 5, 6, and then on 6 we have 7 and 8 attached. We have an ethyl group. So here's the final product, which is, of course, an alpha-beta unsaturated carbonyl compound. So this is the product that would form if we deprotonated on the outside on one of the ethyl groups. But we also need to think about what would happen if we deprotonated on the other side. So in the middle here, let's draw. Here is one carbonyl, 2 carbons, another carbonyl, and our ethyl group. So let's say we deprotonated one of these. If we did that, then it could potentially form a ring here. Here's our nucleophile attacking the electrophile in the same molecule. How many membered ring would it be? 1, 2, 3, a 3-membered ring. So we know that the 3-membered ring doesn't form. So from this starting material, we get one single product, which is, of course, what we're always interested in getting. And we're not interested in mixtures. So let's say we had a target molecule that we wanted to make, and let's think about whether we could make it from a intramolecular aldol reaction. Let's make a 6-membered ring this time, and make a carbonyl outside the ring. So here is our alpha, beta, unsaturated carbonyl, and put a methyl group over here. So we are making this by an intramolecular aldol reaction, reacting sodium hydroxide with what starting material? Okay, so let's draw in the hydrogen here. So it's easy to kind of figure this out. And then let's go ahead and number 1, 2, 3. I'm not going to number through the double bond because this is the new connectivity. I'm going to number through the original molecule. It'll just be easier. 5, 6, 7, 8. And then we'll call this methyl group hanging off there 9. Okay? So thinking backwards, this is the new bond that's formed. It used to be, on carbon 8, that used to be what? That used to be a carbonyl. That used to be an aldehyde, right? And so we can now figure out the product. 1, 2, 3, 4, 5, 6, 7, 8. So if I draw that, 2, 3, 4, 5, 6, 7, 8. And again, number it. 1, 2, 3, 4, 5, 6, 7, 8. You can do this without numbering, and your chances of making a mistake doing that will probably be about tripled, if not more than that. So beginning, here is carbon number 2. It's got a carbonyl on it, and then carbon number 6 has a methyl group hanging off of it. That's 9. And then carbon number 8 used to be carbonyl, and a hydrogen used to be an aldehyde. Okay, so this is our starting material, and so carbon number 3 is going to be forming an enolate, and that's going to be attacking carbon number 8. So the question is then, is this a good reaction? We worked backwards from our product to what we want to start with. Is this a good reaction? And it is a good reaction if it gives only one product. Does this give only one product? Well, let's look for, here's our alpha hydrogen, or alpha carbon right here. There's another alpha carbon there. What if this enolate formed? Then that could also attack over here. And if it did, it would form a 1, 2, 3, 4, 5, 6, 7, 8-membered ring. So we don't need to worry about that. What about this alpha carbon here with these alpha hydrogens? If this dot deprotonated, then that could attack this carbonyl and 1, 2, 3, 4, 5, 6. So that would also form a 6-membered ring. And so we are not going to get the only product that we want. We're going to get another one. So let's go ahead and draw the product that forms in this competing reaction. So go ahead and turn off or pause the video and draw that product, and then come back and see that you have the same product that I have. Okay, so what's the other product going to look like? We already said that 7 attacking 2 is going to form a 1, 2, 3, 4, 5, 6-membered ring. So if I'm drawing that, I am making a 6-membered ring and numbering it from 2 to 6 because these are the, 2 to 7 because these are the atoms that are going to be part of the ring. 2, 3, 4, 5, 6, 7. And then what do we have? So attached to carbon number 7, we have the aldehyde carbon hanging off. So we have carbon 8 over here. And then carbon 7 is attached to carbon 2, and that's the new bond that's formed, and so that's the carbon-carbon double bond that's making the alpha-beta unsaturated carbonyl. Then we are going on around the ring here, 3, 4, 5, and then on carbon number 6 we also have a branch. So we have carbon number 9 hanging off there. So the product that we want is this methyl ketone, and the competing product that also forms is this product that has also a 6-membered ring, but it's got an aldehyde hanging off of it and a methyl group in a different position on the ring. Okay, so we can use this reaction in synthesis, but if we want to use it in synthesis, then we go ahead and draw the starting material, then we double check and make sure that that starting material will only give the product that we want and not a competing product. Otherwise, this isn't a useful synthesis.